Stand here. All right. All right. Thank you everyone for coming to the thesis. God, I missed my mark already. Thank you everyone for coming to the thesis defense of Thi Truong. Thi is going to tell us in a little bit about some of her results from Kamaʻehuakanaloa. I have to get the pronunciation right. Kamaʻehuakanaloa, and I have been practicing that all week to myself, so I'm sorry. Otherwise, formerly known as Lōʻihi Seamount. Thi has been at OSU since 2017, but came to us after getting BA, BS, and an MS degree at UC San Diego. And while here, she's received a number of awards. I've put a list of some of them up there. They include, just last night, receiving at the CEOAS award ceremony, the Outstanding Teaching Assistant in Geology for 2023, which is great. And Thi has also been a real stalwart of both outreach and work on diversity, including being a founding member of the Unpacking Diversity Professional Learning Community, which did a huge job in helping our college and also our discipline address issues of diversity, equity, access, belonging, things like that. Anyway, so I think without further ado, I'm going to leave the camera alone because I've never been good on the camera, and ask Thi to talk into the green light and tell us a little bit.
I have my own green light. Thank you so much.
You're good, thanks.
All right. Make sure my slides are advancing. All right, hi everyone. Thanks for making it here today. The title of my talk is Revisiting Lōʻihi, Geochemistry of Kamaʻehuakanaloa Lavas, Reveals Complexities in the Pre-Shield to Shield Transition and Hawaiian Mantle Plume Source. A lot of moving parts to that, but I'll explain them one by one. Thanks, Adam, for the introduction, by the way. I just wanted to give everyone some reminders. So in person, thanks everyone for wearing masks today. I really appreciate it. I want to let you know there's a recording in progress of myself and also the audience. There's a camera over there. I can see all of you. That's fun. For purposes of just access, we will use wireless microphones during Q&A. So that means if you do have a question, like during the talk, I'm going to have Jen pass you a microphone before you ask it. If you ask it before, you'll have to repeat it. For the folks joining us on Zoom, we're not letting people unmute today. However, you can submit your questions to the Q&A box. You can also use the chat box, but I might miss it because sometimes it moves pretty fast. There are captions available. If you click the Show Captions button, you should be able to enable it. If you need any help during the talk, you can message co-host Emily Cahoon. And then if you're tuning in from YouTube, we don't have any chat, and live captions aren't available, so if you need them, just please make your way over to Zoom. If you have any questions about any specific slides, you can use the title numbers in reference, or I have slide numbers on the top right. But it's okay if you forget those too. Okay, so my talk is about one of two major types of oceanic rocks. I know that a lot of geologists or non-geologists kind of think of the ocean as like a bathtub where like sand goes to the bottom of the ocean. It's actually mostly igneous rock. And it's usually two types of igneous rocks that form from two different processes. So I'm going to explain them to you today. The first one is the mid-ocean ridge kind of feature, tectonic feature, produces something we call mid-ocean ridge basalts. They are the most common type of rock on the seafloor. They make up the majority of the rocks, and basically they underlie all the world oceans. The volume of how much we have from those and the chemistry of them suggests that they are from the upper mantle portion of the Earth, so the Earth's interior, that comes up and melts and then produces these rocks. So mid-ocean ridge basalts, or MORB or MORB, make up the majority of rocks on the ocean floor. At some special places, you have oceanic islands. These pop up in the middle of tectonic plates, so they're not produced at the same kind of boundary that you see from mid-ocean ridges. Collectively, we just call those OIB, which means ocean island basalts. So I'm going to use the word OIB to refer to these and MORB to refer to the other ones. Because they're not produced at a ridge, they're considered intraplate or within plate. In contrast to mid-ocean ridge basalts, their chemistry and characteristics suggest that they are from an even deeper portion of the mantle, so still a solid mantle, just a deeper portion of it. And I'll go through some of the reasoning for that. But just to review this, let's say we look at the Pacific Ocean. We have mid-ocean ridge basalts being formed at specific places, and then we have just other MORB, just older MORB, all throughout the ocean. So on this figure specifically, the mid-ocean ridge basalts range from 0 age, being freshly made, all the way up to 180 million years. So a lot of history there. And then if we want to contrast that with OIB, it's a pretty small portion of them. So this has been noticed by geologists for a long time. You don't even have to go to the bottom of the ocean to see this, but OIB are a lot rarer. And now the geochemistry of those reveals a lot of information that you just don't get from mid-ocean ridge basalt. So a lot of people say there's a disproportionate amount of information offered in a small amount of lavas. Okay, so just to review why this is important, I have a picture of Venus on the left and a mystery Hawaiian volcano on the right. Both of these are basaltic intraplate volcanoes, but one occurs on another planet. Some early research this year found that there are actually mapping evidence of active lava flows on Venus at a specific place. And at this mystery Hawaiian volcano, we haven't had such luck, but it's on our planet. What's interesting about these types of lavas, or these volcanoes, is they can be really tremendous and huge, but we still don't really understand their making. And one hypothesis about their origin or how they're made is the mantle plume model. And this cross-section shows kind of a schematic that just shows a thermal anomaly at depth is hot enough to rise buoyantly as a solid package. And then when it's shallow enough near the surface, it can melt and then produce these large volcanoes. So that's kind of the explanation for OIB, their creation, and it's relevant not only here, but also on other planets, because no other planet has plate tectonics. Okay. And the mystery Hawaiian volcano that I showed earlier is on this plot to the left. This is a figure showing the island of Hawaii, which has more than one volcanic center. So it shows about 5 or 6 on this figure. I'm going to highlight a couple of those. So basically the way that these are created is a plume or mantle plume is stationary, and then a plate moves overhead. That's why you produce a linear chain of islands, even though the plume is stationary. Not only does this create a linear progression in the volcanoes, it also just produces different kind of life stages based on the activity of the plume to melt and create a volcano. So there's kind of a linear progression where you begin with this stage called the pre-shield stage, which is just when it's beginning to be born on the ocean floor. And then it just amasses more lava until it's big enough to enter what we call the shield stage. And this takes about 1 million years at minimum to happen. And from there, after it's created, it is big enough to kind of sink into the ocean floor, and the height can decrease for that reason, it erodes, and then there are other periods of volcanism that happen thereafter for a variety of reasons. But you can have all the different stages on one volcano. So that's shown here on the left side. And yeah, so it's at least millions of years of evolution to create not only just this whole sequence, but individual stages as well. Okay, so the mystery volcano, of course, is what a lot of people have come to know as Lōʻihi Seamount. So it's in this bottom right corner of this plot right here, named, and just a little bit of history about it. In the mid-1900s, there was a lot of exploration of the seafloor and not that much explanation for if volcanoes were active or not. As you can see on this kind of bathymetric map, there's a lot of features near Hawaii, but we don't know if all those are active. Lōʻihi was one of those. It was kind of there, don't know how old it is, don't know if it's active. In 1979, there was a seismic swarm, then everyone kind of realized this volcano should be on their radar. So ever since the 1980s, there's been a ton more studies at Lōʻihi. So there have been one known as an active volcano off the coast of Hawaii, makes for really great expeditions on the way to another Hawaiian volcano. There were helium isotope studies, which I'll go over later. And then there are basically more seismic activity that resulted in a rapid response cruise. And then more recently, the name was changed to another name to more accurately reflect the Hawaiian tradition of giving place names, especially to volcanoes. So the new name is going to be Kamaʻehuakanaloa. So in addition to kind of revisiting this volcano as a new name, I want to revisit the rocks that we found there. Even though it's been studied extensively since the 1980s, I think there's a lot that is worthy of revisiting here. So that's Lōʻihi, or Kamaʻehuakanaloa. I use Kamaʻehuakanaloa, but I know some people might not remember it. So if you use Lōʻihi today in the chat or in person, I also understand what you're saying. Okay, so some variation about this volcano, which is, by the way, as we saw, it's a pre-shield volcano. It's the earliest stage. It was actually the discovery of it proved that the pre-shield stage indeed exists and has a certain composition. So it's one of the only kind of good exposures we have of that early stage. So thinking about that in terms of just as a volcano, that's why it's important. And then if we just look at spatial variability, the characteristics of what it looks like, there's that summit platform, which is the highest part of the volcano. It's about 1,000 meters below sea level. In addition, we have these rift zones here. The south rift is the longer one, I think it's about 14 kilometers long, and the north rift is a lot shorter. But the south rift is kind of the most obvious feature that we see that's kind of like elongate as a rift zone, and the north rift is just above the summit. Another feature is on the east side of the volcano. It's very steeply sloped. So if you took Geo 101, you remember your contour lines, very steep area that's basically kind of eroded and been deeply dissected. And then on the other side, it's kind of a more gentle place called the Western Ridge. So those are kind of the 4 locations that are present even at this volcano that seems like it kind of just doesn't have a lot going on. Okay, and then this is a diagram of the geochemistry of this volcano. And so I had mentioned that this volcano was proof that you could have compositions of what we would say like basanite, alkali basalt at the pre-shield stage. So that had not yet been discovered at this volcano. And basically, if you want to think about it in terms of evolution, we have this composition for pre-shield that we usually liken to basanite alkalic transitional. So that dashed line is kind of the dividing line. Anything above it, alkaline. Anything below it, subalkaline. Actually giving those rock names to the samples is not just a chemical kind of process, but also modal abundances, so you have to count minerals as well. So this is not the whole picture, but it's very approximate to how we deal with these rocks. So the earliest stage of this volcano being born, we think of it as happening with those compositions at the top. And then once you get to the bigger shield stage, it's more like these compositions on the bottom. Okay, I'm also interested in this little transition, so I highlighted it in blue. If the pre-shield stage is usually buried, and then the red tholeiites are just high volume, what is there to find out about the stage in between? As you can see, there's something called transitional basalts, and the degree to which those are really part of the transition is not really straightforward. So I would like to investigate that more. Okay, so the chemical compositions roughly correlate to the shield forming stages, and I'm curious about this early volcano being at such an early stage, how variable it is as it goes into the relatively larger volume stage. Okay. So for this study, I revisited the evolutionary history of this volcano by looking at 64 samples from 5 different expeditions, and also integrated some literature data to try to think about producing coupled data sets of key samples. So my first chapter relates to this pre-shield to shield idea with major elements and asking if the classification is supported by trace elements, especially for those transitional basalts. What information can we gain about the pre-shield or shield stage from these kind of in-between compositions? The second is about helium isotopes, which have been really important at this volcano just since the 1980s. And even though this evolution has been devised for major elements, like major rock-forming elements, there's really no model for how helium isotopes fit into that, except that they definitely decrease at some point. And usually when it's the large shield stage, but not really for this kind of pre-shield to shield idea. The last chapter relates to lead isotopes, which are radiogenic, which is in contrast to the helium isotopes. And they kind of glue together the insights from trace elements and helium isotopes to think about the mantle source. And just related to the idea of chapter 2 and chapter 3 is, what can we know about the plume? Not only just its general characteristics, but if it has changed from pre-shield to shield stage, if it has at all. So this slide is about basically the typical coverage of this volcano to date. And I do want to say this is a GeoRock database for just whole rock data, which is pretty common nowadays, but I'm using it as kind of an example for how well we've studied this volcano. But there you can also measure glass and minerals and that stuff. Okay, so this is a GeoRock database search that you could do today and it'd have the same results. I have the sampling technique as dive, dredge, outcrop, rock core. The predominant types of collection are dive and dredge. So dive is in the red circles and dredge in the green triangles. So as a whole, dredges are useful for collecting a lot of material along a known slope, and then dives are favorable for kind of targeting outcrops, but they collect a lot less material. So just looking at this map of this volcano, there's a lot more dredges, and the dives are kind of in different areas. But there's also probably issues with just reporting all the data for the right samples in GeoRock, so it's not the complete story. Okay, so for this study, I'm targeting the different locations, and not only those, but also different collection methods. So for example, we have the North Rift dredge samples, and so these are collected with huge hauls. There's more dredges at the Western Ridge and a few at the South Rift. And then at the South Rift, we have mostly dive samples, and then this is a video showing what a dive collection looks like at, say, 4,300 meters. So most of the samples come from the South Rift, and the reason why we did that is because it's a long rift zone that should kind of track volcano growth, because right now it's hypothesized that it kind of grows south to north. So you should be able to get maybe some information about its growth, though within the individual rift zone is not so clear. Something else I want to mention is that although the cartoon of like the evolution looked really clear, at this volcano, the compositions kind of interbed, and it's really gradational. So that introduces another challenge. Something else I want to note is that when we're talking about dredges are great for volume, dives are not, like that is literally the only sample volume we get for that area. So that sample fits in like a 1-quart Ziploc bag. You can bring it through TSA. And then for the dredges, it's like hundreds of kilograms. So sometimes the replication or like reanalyzing the same samples is made difficult because there's just not enough sample to work with. Okay, and then something else I want to note is that for this dissertation, I only analyzed the glassy portion of basaltic rocks. So it's the really cooled outside layer when it hits seawater. Okay, and then I'll go over this workflow, but the key idea is that starting from the yellow box, glassy pieces chipped from the basalt rind, there are different aliquots or subsamples that sometimes go through the same line of analysis, and this is good for making sure, there will be sample variability, but it's good for kind of making sure that, we have the same sample that we're working with to get the same information. So chapter 1, which I'll start with next, is about trace elements, which we measured here at OSU. And then the second chapter is pretty involved, has a lot of volatile elements, so that would be helium, CO2, water, and I will just focus on the helium isotopes here. And then chapter 3 is the lead isotopes. Okay, so trace elements. So just to remind you about the main question was thinking about this pre-shield to shield stage variation. So in addition to just the major elements, what about the elements that are kind of sensitive, occur in smaller proportions? What do they say about this transition? And the method is in situ, so in place. So actually taking samples and analyzing like lines along the glass. And those pictures up there, it's about the epoxy mounts are about 1 inch in diameter, and those are pretty zoomed in. But the glass is pretty nice for making homogeneous and like precise trace element analyses. Okay, so this should be scary to anyone who's not a geochemist, but I'll try to explain it. This is kind of all the trace element kind of results that we get for each of these lavas, and I've split them up by major rock type. So basanite first, alkali basalt, transitional basalt, tholeite, and then we'll have tholeites from the North Rift at the end. So this kind of tracks with this progression from pre-shield to shield. And well, the first question I wanted to ask was, how do transitional basalts how do they plot? Do they plot more with alkalic or tholeites? And in this diagram, they seem to plot more with the alkali basalts, though the alkali basalts definitely have a lot of variation. And then we see that the samples that have the most enrichment in incompatible elements is basically like the top line vertically in the basanite section. Those show the most enrichment in incompatible elements. On the bottom, we have both of the tholeite kind of suites, though the North Rift is really limited. What's interesting about these is that on the left side, you have all the South Rift tholeites, and they kind of plot towards the bottom, meaning kind of less enriched incompatible elements. And then for the North Rift, it actually plots at the most minimum of all the samples. So even compared to the South Rift tholeites, they show less enrichment than the South Rift ones. So that's kind of one way to look at the variation among these lavas. I have these vertical lines, which I'll return to later, but they basically represent anomalies in elements, and we're just looking for if it goes up or if it goes down relative to the left and right neighbor. Okay. One way to investigate kind of the enrichment in the basanites and the alkalic basalts, which we saw in the upper left, is to see how much they were crystallized. Even though they're basalts that are hot and come from this hot mantle plume, they still can crystallize slightly when they're being formed. And so this modeling is meant to estimate how much crystallization happened even when the glasses were being formed. They look really glassy. So this uses a composition from Kilauea at Hawaii. The starting composition is on the right, so starting composition. And then crystallization basically proceeds as you go to the left. And I have some dashed lines here at MgO values on the x-axis. And basically up until, so from MgO equals 16 up until MgO equals 6, it's basically only olivine crystallization. And then past 6, you get CPX. And then past about 4, you get plagioclase. As you can see, there's some good overlap between the model and my samples. But the iron and also not shown here is the titanium tends to be elevated at this volcano, and this is kind of persistent across studies. Overall, though, if you kind of interpret the model results for how they are, it's about 25 to 35% crystallization maximum to have occurred in these glasses, and this can concentrate the enrichment for incompatible elements, at least in the samples that are like the yellow triangles, the alkalic samples. Okay. Another aspect to figuring out if the incompatible elements are due to shallow processes like crystallization or something deeper like the mantle source, we can model mantle melting. So between two potential compositions at the same time, garnet leurzolite, spinel leurzolite, basically two predominant mineralogy in the mantle that produces oceanic rocks. The main thing to keep in mind is that garnet leurzolite has minerals that basically occur a little bit deeper than spinel is shallower. So if we kind of go through basically the progression from what we say pre-shield to tholeiites, the two basanite samples are kind of plotting in different places, but they have about 2 to 10%, kind of the lowest. And then we kind of proceed through this kind of trend where they keep plotting kind of more towards spinel leurzolite, and then the percentages of melting also increase. Then we kind of finish with the North Rift. It's about the same thing that we expect. So all the compositions put together kind of show differences in melting that produce them based on this model, and then potentially differences in depth. So just to review, the percentage of melting of the mantle to produce the first magmas that produce these, this is deep, is really low, up to 5% for basanites and alkalic basalts. And then transitional is kind of 4 to 10%, which kind of overlaps with the tholeiites. But there is variation within the tholeiites as well. So the North Rift has 10 to 15, and the South Rift has 5 to 15. Again, the caveat is there's pretty limited samples, but it seems quite distinct, at least just from these. Another potential indicator of depth of melting is a ratio like samarium ytterbium versus a major element indicator. In this case, we use potassium over phosphate. And if you just look at the y-axis, you can see that the rock types kind of differ based on that indicator. And then if you look on the x-axis, there is a trend from samarium ytterbium. Towards the right, the alkalic basalts tend to be more positive values or higher values, and then the tholeiites are on the left. So you can see this even at the South Rift, which kind of has this gradation, And then you can see it even when you don't have that many samples from the east flank, the north rift, and the western ridge by itself. So yeah. So just to review the rare earth element modeling, then like the indicator for lithospheric thickness, we have basanites, alkalic transitional basalts kind of being produced at higher depth with less melt. And then the tholiites have more melting, and the north rift is potentially the highest degree of melt that we see from these samples. Okay, so overall, the trace elements, So overall, the trace elements do show that there are differences in the way that the lava compositions were produced at different locations along the volcano. There could be shallow processes like crystallization, and then there could be mantle source variation, which would occur before the fractional crystallization. So then assuming kind of this growth model where there is maybe a south to northward growth trend, it looks like that heterogeneity is still preserved even as the volcano is proceeding to produce tholiite lavas. So I would propose that even though the shield stage is pretty homogeneous at most Hawaiian volcanoes, that isn't really the case here, and we can expect to see more heterogeneity as the shield stage progresses. The north rift tholiites seem to have distinct geochemistry, and it appears to be a distinct mantle source. This had not really been explored yet in previous studies, and part of that is because there's a lack of coupled metadata with basalt samples, so there have not really even been attempts to integrate the different locations and just kind of treat it as one volcano. But it looks like the trace elements suggest there's different sources. So kind of following the line of reasoning for what the differences are, we will look at helium isotopes. So the workflow I showed had a bunch of different volatiles, including CO2 and water, but I am just presenting helium isotopes today, and I'm going to present them based on this ratio, helium-3 over helium-4. So on the left, you have helium-3, and then on the right, you have helium-4. And the idea is that helium-3 is a primordial isotope, so it was produced in the Earth during accretion, and it's not created by any other process, whereas helium-4 is produced by radiogenic decay as an alpha particle, and the ratio, the radiogenic isotope, is on the bottom. And so there could be some variation in the ratio due to what goes into helium-3 and what goes into helium-4. Luckily for this volcano, because it's underwater, helium-3 is really only magmatic, so it's not produced by any process that seems to plague the volcanoes on land. So that just leaves us with helium-4 having radiogenic inputs and having magmatic inputs. So going over this helium isotope ratio, I'll use the unit Ra to refer to how big this ratio is. And generally, the mid-ocean ridge basalts that are the most common basalts on land are basically 8 to 10 Ra, and then the ocean islands are about 10 to 50, so they range a lot more. I just wanted to say that this helium isotope value is one of the criteria we use to say a hotspot came from a deep mantle plume. But as you can see from this table, it's pretty variable. Not available, low, high, high question mark. For Hawaii, it's really good. Everything looks really great, mostly. But typically at Hawaii, we have really high helium isotope ratios, especially at Kamaʻehuakanaloa. And since the 1980s, it's been a great kind of like model composition to use when we want to say, this is an OIB with a deep mantle plume origin. Let's investigate kind of the geochemistry. Hawaii's been a great example for that. Okay. And I mentioned targeting the magmatic signature for helium isotope ratios. So helium isotopes can be done in minerals, in lavas, in rock, and they're usually in these inclusions that are captured in glass and olivine. The thing you want to be careful about with minerals is that the minerals should be phenocrysts, so olivine or something should be formed in equilibrium with the melt and not just carried by the melt later on. That way, you know that your helium isotopes are actually indicating like the magma. So for this study, we have targeted basaltic glass to make sure it is actually a magmatic value. Because it's been frozen in by being quenched, the idea is that the magmatic composition is preserved. You still have the fluid inclusions. We'll call those the gas. So they're kind of trapped bubbles. They're in red on this figure. And then the melt is like just the glass itself, the black stuff that you see. That's basically the melt. So we have two kind of components, and we can measure helium isotopes on both components. So just to show you what that might look like, here's that nice workflow diagram. We'll get basalt glass pieces from the same basalt rind, and then with the glasses, like you see in this picture, that will be what's used for the entirety of the study. So we collect some glass, crush it, and it becomes this powder. And in the process of crushing it, we've also separated the helium, and we can measure helium isotopes on this fraction, and we call it the gas fraction. So those red bubbles you saw in the first photo, not actually red, it's just false color, but it's those bubbles. So in the process of crushing this, we release the helium that was in there. So after that, we take the powder, and then we load it in little tinfoil boats. So it's a pretty arduous process, literal tinfoil. You have to kind of make a little cup, and then you have to put the rock powder carefully in the cup, weigh out how much you used, and then put it in a furnace. So the furnace is at 1400 degrees Celsius, which is like, Elmo temperatures, I think. Okay. This is an example of what those two processes get you in terms of results. So the yellow squares are crushing values, so that means the gas fraction. And then the black diamonds are melted helium isotopes. So you can see there's actually a difference. Sometimes you get really good agreement, sometimes the melting is a lot lower. And this is to be expected, but this is the purpose of doing these two different measurements, is to be able to figure out what is happening in this magmatic system. Okay, going back to this, just letting you know that the crushing value that I mentioned on the first slide, if that's the magmatic signature, that's the one we're using for the talk. So that would be the vesicle, helium-3, helium-4. So that's what I mean when I say that. Overall, the helium isotopes are in range of previous studies. It's kind of what we expected, but there is an interesting correlation with the rock-forming elements. And this proxy we use is called the alkalinity index. So we have tholeite, transitional alkali, and there seems to be a negative relationship. In addition, if you just look at South Rift lavas, because there's a good number of them, the mean helium-3, helium-4 is statistically different between tholeites and transitional and alkali basalts. So the tholeites are definitely higher, transitional alkalic pretty similar. So overall, helium isotopes seem to track some kind of petrogenesis from the early alkalic and transitional to the later tholeites. And then this is seen also within just the South Rift. Okay, and then going back to the crushing and melting differences, what's nice about those differences is they can actually be used to calculate post-eruptive age. So when I was talking about the helium-3 over magmatic or radiogenic helium-4, this basically utilizes the radiogenic helium-4. So you can actually use their difference to calculate potential time that they've been sitting on the seafloor after eruption. And you get ages up to 24,000 years due to the high uranium thorium that's in these lavas, basically in the melt phase. And this is consistent with previous calculated ages for a sequence that had stratigraphic control. So useful to see the difference between the two. And then this is going back to the trace elements, but there have been proposed relationships between these positive anomalies in these three elements and helium-3, helium-4. And if you plot the South Rift data and the North Rift lavas, there does seem to be a good relationship between this tantalum anomaly and helium isotopes. So more evidence that not only high helium-3 is preserved, but also there could be recycled materials in there. Okay. And then this goes back to the trace elements. So that were in the previous chapter, but I did want to mention that there's increasing evidence that there's a relationship between tungsten isotopes and helium-3, helium-4, and this is related to basically the metallic core. So that would provide really good evidence for deep mantle origin, because you really can't get any deeper than the core mantle boundary. And I just wanted to show some results from the tungsten results, so not helium-3, but just tungsten. The ratio of two kind of incompatible trace elements is in good agreement with previous values. So my data is in these plots, and then the previous value for this volcano is in the red dashed line, and then Hawaii is in the blue dashed line. Kind of within range, although we see some variation within each rock type. And then finally, if we kind of look at mantle source characteristics of tungsten, there's this trend we get from high helium-3, helium-4 lavas, and usually they're kind of anchored towards what this Lōʻihi volcano says. And previously, we have precision, or at least known values for Lōʻihi of 11 plus or minus 5 ppb for mantle source tungsten. That was from 6 samples. So if I get the average kind of from our samples, it seems to be a lot lower, even closer to the depleted Moore mantle, which is kind of interesting. So overall, helium isotopes seem to correlate with the major elements. There's evidence that if the tholiites have higher helium-3, helium-4, then they are not decreasing even if there's higher volumes of melting. And then the North Rift is still showing some distinct values relative to the other samples. Okay, the lead isotopes, I know I have to hurry up soon, so we'll just go through this pretty quickly. Lead isotopes, these were done on chemically digested samples, still glasses, but they go through a little processing. And the main idea for lead isotopes is to try to answer the question of how does this new volcano relate to this really old trend? So it's called the Kealoha trend, which is kind of observed at Hawaiian volcanoes. Basically, red color in these graphics will be Kea trend. Then blue is going to be what we call the Loa trend. And basically, the Loa component, if it's seen in the geochemistry of rocks, is hypothesized to be related to the plume. And then the Hawaiian Islands forming, the main Hawaiian Islands forming, see both compositions at the same time, just at different volcanoes. Okay. And in this model of how a plume might internally look different for chemistry, you could have at basically the vertical conduit, some mixing of these two components at the same time. Notably, at this volcano, the helium and lead isotopes so far appear Loa-like, but previous studies show that strontium and neodymium are actually more like Kea, so more like the red color. So the question is, where does it fit onto this kind of idea? So just going over some results really quickly. So my lead isotopes are shown here, and then there's previous values shown transparent kind of colors. And there's variability with latitude. And I just kind of use this as a proxy for location. So the South Rift on the left shows a lot of variation, kind of similar to a stratigraphic sequence in the pit craters. And the North Rift is pretty different. So comparing this with the cloud of previous data for this volcano, it all fits in pretty well into that cloud. Pretty big cloud. The other thing I want to note is that for rock types, the alkali basalts kind of have their own little cluster, then the transitional and tholiites have their own other cluster. So there have been suggestions that individual volcanoes have lead isotopes that can actually go either way. So as they proceed with age, they can either go more radiogenic or they can go less. This has been proposed to be related to Loa Kea components, but it's pretty unclear right now. But we do see there is kind of this clustering. Okay. And then kind of going to Hawaiian Shield context, they definitely plot with the Loa side. So that line, anything above it's Loa. So pretty consistent with what was previously proposed. And even with this alkalic to tholiite trend, you still stay on that side of the Loa trend. Another aspect to this Loa Kea idea is looking at this calculated ratio, which is called the radiogenic 208 lead over 206 lead. And basically, there's also this Loa Kea dividing line. And previous data was pretty much all above the line. This study shows some variation, and some samples actually plot below the line. Those sample types are wrong, by the way. There's no basenites. I messed that up. It should be alkali basalts, transitional tholiites. So it's still mostly Loa, but maybe some samples, alkalic samples, probably cross over to Kea. Okay. And then for the global OIB context, it's kind of firmly in the Hawaii field. Not really much else to say about that. There are some ideas that there could be some recycled components that make you go left or right. But for global OIB, that's what is shown. And then another exciting result is there does seem to be a relationship between vesicle helium-3, helium-4, and then lead isotopes. So all the lead isotopes actually show a pretty good correlation, but this is 206. If you just concentrate on the South Rift basalts, there seems to be a positive relationship. And previous studies have even integrated this with stable isotopes. So the whole system, helium isotopes, lead isotopes, stable isotopes, they all seem to suggest that there are surface and deep processes that are being recorded at these lavas. And this is really valuable when you have the same studies being studied across different labs. and then you can integrate them together. So this is the big conclusion slide, and I'll show it to you again. But basically, the broad trends suggest there are shallow and deep processes that produce these compositions. Helium isotopes, which have been really central to thinking about this volcano, indeed seem to correlate with kind of major elements. The South Rift is pretty variable, but it's consistent kind of within its suite, like it's evolved together. Then the North Rift seems to show something that's slightly different with limited samples. And overall, for evolutionary stages, it appears that there is an evolution that we can track between alkalic to tholite basalts. And if you want to use kind of the southward to northward growth model, helium-3, helium-4 seems to be staying high or increasing with higher volumes of melting, and it's definitely not decreasing with mixing towards morb. And then overall, it seems to be consistent with low component if you use the bilaterally zoned plume model. Yeah, and then if we want to say kind of a takeaway for data management, sometimes you have like 100 samples you start with, and then you use like 2 to like model variation in the world. That's fine, because you just have to do that sometimes. But there are just some aspects to which there are samples that are collected in the 80s that kind of don't make their way to studies, in the 2020s, and that's pretty interesting. So I hope that this kind of analysis of samples at this volcano, which has been studied in the 1980s, kind of shows that revisiting the data produced by a lot of different data sets is pretty worthwhile. Lastly, I do want to note that the OIB kind of geochemistry method has benefited so much from the Hawaiian volcanoes and other Pacific islands, and this is also just something shared by the public. We have a lot of tourism at Hawaii, and we have a lot of history of kind of spectacle, especially related to volcanoes. So this is evident by a newspaper clipping that kind of advertises this hotel that became part of HVO later. You can enjoy this volcano all throughout the year. And I do want to just question how much the outcomes really benefit the local community. Do they benefit as much as we do? Question for the future. Okay, acknowledgements. Definitely my funding sources, NSF, GSA, ARCS, Elizabeth Peter Leone, and then the folks at University of Hawaii and Scripps, and then the research groups here. So this is kind of my big thank you slide. I do want to thank everyone here at CEOAS, so everyone who's helped me, faculty, staff, postdocs, other grad students, other people in the geoscience community, and my friends, and yeah, that's it. Okay.
So now in this part of the session, we'll take our questions before we move to the private part of the thing. But do you want to leave questions?
Yeah, in general, yeah. Yeah. Are there Zoom questions? Okay, we can start with Zoom because Emily has, yeah.
From our wonderful alumni, Nicole Rocco.
Oh, hi, Nicole.
She was wondering if you could speak to the tungsten results and why you think they trend more toward morb values.
Oh, tungsten. Yeah, that's a good question. So one is the selection process that I used. So I used samples, this is a mantle source calculation, so I used samples that only crystallize olivine, so they're relatively primitive. Previous studies have said maybe our samples have been enriched by some process because they've been underwater. That could increase kind of like the incompatible elements you have and could make for a higher value. So I used, I think, just maybe more primitive values than they did, the tholiites. But I do want to note the North Rift tholiite is super not enriched, and that just hasn't really made its way to any studies, so that could be part of it. Okay, any in-person questions? Okay, Daniel?
I have a question about what's the resolution quality on the ages from the helium estimations?
Oh, the ages. So it's probably a couple thousand years. So it's only efficient on some samples that have enough thorium uranium. So there's some like indicators for just the thorium uranium ratio that you want to use. We kind of interpret them kind of in the 1,000-year precision, but yeah.
I was kind of curious if there was any kind of where you could get results, get progression, or just see it. Does the age of the eruption or whatever from those analyses kind of correlate with progression of the volcanic building sequence?
Yeah, it's tough because even the dive samples, you really don't know relative field relationships.
Yeah.
So it's really one tool, but unless you have good field relationships, it's pretty hard to say what came before the other, especially because with dive samples, they could have still fallen downhill. So it's a little hard to say.
Yeah, because with most of the Hawaiian lavas from like Kilauea and Loa, there's been studies that show that the isotope compositions can range wildly in,
Yes.
in a relatively short amount of time.
Yeah.
So when you say something, it's like it gets more radiogenic over time, but in a short period of time, it can actually range, go all the way from like a K end all the way to a Loa end, and so it makes it very difficult. I'm just
There's like there's simultaneous like broad variation, but it's true like one dredge hull could have like a ton of variation. So it's kind of this issue I think facing all of geochemistry where there's complex variation kind of at every level, and it's a little hard to tease out, especially with mostly dredges or mostly dives with not that much documentation. Any online questions? Nope. Any more questions from students?
Questions in the room?
Okay. Absolutely. Yeah.
For you anyway. So my question is, like when you think about other parts of the world, or like maybe other like policymakers or that kind of thing, what would be the quick way that you would say why they should care about this?
Well, one is the collection of geologic data, like in the large scale, has only been since like the 1960s. So there's kind of no excuse if there's not a modern way to access that data, especially if like data embargoes have expired, all that stuff. So I think like we're in a good position to make sure all the data is accessible, especially if you can't even go to some volcanoes to study them. How do future students get to study them? If they have to deal with kind of chasing down old papers and seeing how everything fits together, it's worthwhile, but it can take a lot of time. Yeah, I think accessible data is a really important aspect of this.
I'm going to be selfish, and this is coming from me first. From a sample management and data integrity standpoint, I thought your analytical workflow figure was super helpful, and I loved that. From Kelly Wall, also alumni, can you talk more about how you constructed your mantle melting models?
Yeah, I can do that. So those are basically mineralogy of peridotites. So garnet, olivine, CPX. Well, okay, so garnet, olivine, CPX, and then some aluminum-bearing phases. And basically, it's just kind of a standard composition that everyone uses. So there are possibly other sources that are part of this, which would be peroxide sources. So I didn't go into detail about that. So I constructed this by basically getting known compositions of those two rock types. And then you calculate with batch partial melting what the potential compositions are. And you can kind of make tie lines for the same amount of melting, 0.5%, et cetera. And so it's really just constant partition coefficients and proportions of minerals. And then you get this result. Because it's a ratio of incompatible elements, I use the results straight from the data. But if you normalize it, it would be the exact same ratio plotted here. Any in-person questions? Oh, wait, sorry, Emily? Okay, one more from Zoom. Okay.
Right, another, I think alumni, I think this would count as alumni, from Penny Weiser. What proportion of all Lōʻihi samples are actually in repositories like Smithsonian that people can access versus individuals having them? Should they all be given, or all be given how the dredges drilling were funded?
Yeah, so it's tough because like the peak of activity to explore the volcano is the 1980s. So they're pretty old collections. And as far as I know, they're mostly in the University of Hawaii repository. A couple splits go to like Japan, Australia, United States. So they're kind of everywhere. And the Smithsonian's starting to get more samples as people kind of leave their collections with people. They make their way over there. The degree to which there's like documentation with them, I doubt it's that much. Otherwise, we'd probably see it online. But they're making their way over to some repositories, and you can connect a lot of dots really well, but you have to go beyond just GeoRock, just EarthChem, just the Noble Gas database. You have to actually just go into papers and really dig at the tables that don't have OCR and stuff. So yeah. Thanks for the question, Penny. Okay. Any more questions? Okay. I guess that's it, right, Emily? Cool. All right. Thanks, everyone.
Then we'll take a 5-minute break and then we'll convene.